Hi, welcome to this video on chemical equilibrium from the OCR spec. We'll cover dynamic equilibrium, Le Chatelier's principle, catalysts, and then the equilibrium constant, or Kc. So I'm just going to start with dynamic equilibrium. And I'm going to abbreviate equilibrium just to this interesting symbol. So, if we take a reaction, and I'm just going to take the Born-Haber reaction, so nitrogen plus 3 hydrogens goes to 2NH3. So, in this reaction, which I'm just going to use a slightly wrong arrow just to begin with, our nitrogen and hydrogen react together to form ammonia, and ammonia can actually then go back and break down and form nitrogen and hydrogen. But at the beginning of this, so I'm just going to create a little time column. So at 0 seconds, I'm going to mix together 10 moles of the nitrogen and 30 moles of the hydrogen. I'm going to have no ammonia at this stage. So this is why this arrow is like that, because this is not at equilibrium at this stage. And we can spot that if we give it 10 seconds. So add on 10 seconds, and then we can measure how much we've got of each. And after 10 seconds, I spot that I've got 8 moles now of the nitrogen, 24 moles of the hydrogen, and I've produced 4 moles of the ammonia. So this definitely wasn't equilibrium, because if it was an equilibrium, then if we left it 10 seconds, the concentrations or the amounts of each would stay the same. So we give it another 20 seconds, see if this is at equilibrium. After 20 seconds, this has dropped again. And so again, we can say that this wasn't at equilibrium and this wasn't at equilibrium. If I give it another 30 seconds, and now suddenly the number of moles are staying the same, or the concentration staying the same, no matter how much time I'm giving it, then we can say that this is at equilibrium at this stage, because the forward and backwards reactions are the same. So we're keeping the same number of concentration on each side, therefore we are at dynamic equilibrium. Now there are reactions occurring. The nitrogen and hydrogen are combining and forming ammonia. It's just ammonia is breaking down into nitrogen and hydrogen at the same rate, so the concentrations and amounts stay the same. So Le Chatelier's principle is the idea that a reaction under dynamic equilibrium will try to oppose any sort of action you put on it. So it'll try and do the opposite. So, for instance, in this reaction, if we increase the concentration of nitrogen, then the reaction will try and decrease it. So then, by decreasing it, it will shift to the right. So shift to the right, it'll start to produce more ammonia. So if we increase nitrogen concentration, equilibrium will shift to the right. If we were to increase the ammonia concentration, it will shift to the left. So this is Le Chatelier's principle. Because we're putting more of nitrogen in, the reaction goes, okay, well, if to oppose that, I need to then react more nitrogen to lower the concentration of nitrogen, and that produces more ammonia. So it shifts to the right. Same thing here. If we increase the ammonia concentration over on this side, the reaction goes, okay, I need to produce more of this side in order to counteract that. If we increase the pressure, so first of all, we've got to check that everything in it is a gas, and we have. So if we increase the pressure, it is going to want to try and reduce the pressure. So it's going to shift to whichever side has the less number of moles of gas. And on this side we've got 4, on this side we've got 2. So it's going to shift to the right. The opposite happens if we lower the pressure. If we lower the pressure, then it's going to fill up that space, and that pressure that was created is going to try and replicate it. So it's going to shift to the side, to the left-hand side, the side with the most moles, in order to counteract that. Temperature is an interesting one, and I can't quite remember the enthalpy for this reaction. Let's say the forward reaction on this is plus 70 kilojoules per mole. If we increase temperature, so let's increase, then the reaction is going to try and lower the temperature. So it's going to shift to the side that's endothermic. That will lower down the temperature. So if it's plus 70, then the right hand side is endothermic, so it shifts to the right. If we increase the temperature, if we lower the temperature, it shifts to the left. So this is Le Chatelier's principle. Reaction tries to oppose it, and we'll look at concentrations, in which way that shift, pressure, where we look at the number of moles of gas, and increased temperature, where we look to see what the enthalpy is, the forward reaction. So this enthalpy over here, this is the forward reaction. The reverse of that will be the exact opposite, just negative. So exothermic, endothermic. So the other factor that does affect reactions and does affect equilibrium is the catalyst. It's just got no overall effect. So if we were to add a catalyst to this, often use iron, then it does speed up the reaction. But it speeds it up in both ways at exactly the same rate. So let's say before catalyst, we had 10, 30, 20. After catalyst, it will be reacting faster, so the reaction rate would have increased, but the equilibrium will stay the same. We'll have the same amount that are in there. Don't need to rub that out. This is a very important reaction. It makes ammonia, which can be used in fertilizers. Now, I'm going to say that it's endothermic, and that means that if it was to go forward, then it would give off. Sorry, it will take in heat rather than give off. So, within this, sorry, I'll rub that out because without the exact value I might go a bit wrong. So, in this reaction, if we were doing this in industry, we like to make ammonia. Let's say we're doing a reaction and we wanted to increase the yield. We'd want to move in directions then that would create as much product as possible. So in this, as much of our ammonia as possible, and so we want to put things into the reaction that increase the amount of NH3 that's made. So the first one would be high pressure. If we increase the pressure, then that's going to shift to the right hand side. So we go high pressure. It could also be, let's say in this, now I remember, it is a low temperature works in this. This is actually, the forward is exothermic. So a low temperature means it would also shift to the right and produce more ammonia if the forward's exothermic. There is a compromise that's met. They might not often do this in industry though, and that is because high pressure is expensive. And low temperature isn't above the activation energy. So it might not meet the activation energy, which lowers down the amount that you want to react. So, for instance, in the Born-Haber cycle, Born-Haber-Boltzmann distribution even, if we've got our EA there and only a little bit reacting and we lower the temperature, suddenly we've got even less that's able to react. So there is a compromise that's met in industry where they might not go as high with the pressure as they'd like because it's too expensive to maintain that pressure, and there might not be enough to meet the activation energy, in which case they still have to heat it up a bit in order to get an actual reaction occurring in the first place. Next up, we've got the equilibrium constant, or Kc. Now Kc, I'm going to do a standard, well, an abbreviated reaction. So we've got, in dynamic equilibrium, A plus B goes to C plus D. And A requires A moles, B is B moles, C is C moles, D is D moles. So they're balancing numbers, or stoichiometry is represented by the lowercase of their letter. Now the equilibrium constant Kc can be calculated by taking C, or the concentration of C, which is why it's in square brackets. This square brackets represent concentration, to the power lowercase c, so this number here. So if the balancing number beforehand was 2, you'd square it over here. If it was 1, you'd do nothing, you just keep that number as it was. And that's going to be times by the concentration of D to the power of whatever the balancing number is in front of D. This is then divided by the concentration of A to the power A, and concentration of B to the power B. And that gives us a value for Kc. Just to put this into a kind of mock calculation where we can see that, let's say we had A plus 2B goes to 2C plus D, and we had 1 mole of this, 2 moles of this, 1 mole of this, and 2 moles of this. And put this into our calculation. So we'd have on the top Kc equal to 1 squared times 2, because we've got 1 to the power 2 because the balance number in front is 2. D is just 2 because it's got a 1 in front, and so 2 to the power 1 is just 2. Below we'll then have 1 times 2 squared, which will give us a Kc equal to 2 over 4, or Kc equal to 0.5. If the Kc value is greater than 1, so Kc greater than 1, then we can say the equilibrium favours the right hand side. So in our reaction of A plus B going to C plus D, if its Kc is above 1, then it's favouring producing more C and D. If Kc is lower than 1, then it favours the left hand side. So that one where we just saw then, where we had A, 2B, I think it was 2C plus D, that had a value of 0.5, so the equilibrium favoured the left hand side. And that is equilibrium constant and chemical equilibrium.